The goal of this video is to use the idea of conservation of mechanical energy to solve or simplify calculations in physics. Mechanical energy generally falls into two categories: kinetic energy and potential energy. Mechanical kinetic energy is always equal to 1/2 mv squared. Potential energy might come in a number of different forms, depending on what's included in your system. Additionally, work may be done on or by the system under consideration, which will either add or remove mechanical energy to the system, often by converting it into other forms of energy such as heat. Work done is always just the dot product of an external force and the displacement of the object. Kinetic energy is always present if there is motion of the system. If something is moving, count on kinetic energy. Work done requires something external to your system interacting with it, a push or a shove, or the presence of frictional forces. Potential energy always involves the interaction of parts of your system. For gravitational potential energy to be considered, both an object and the Earth are considered to be part of the same system. If a spring is included in our system, we can include the potential energy of the spring being compressed or extended by the other pieces of our system. Conservation of energy says, very simply, that whatever energy is present when I first look at a situation should be accounted for at any other time. Therefore, the sum of all of the kinetic energies in my system, plus all of the potential energies, plus any work adding energy to the system, should be equal to the sum of all kinetic and potential energies later on, plus any work that removed energy from the system. Here's a simple example of conservation of energy. Consider a simple pendulum, which consists of a mass, called a bob, hanging from the end of the string. Initially, the bob has no energy at all. If we pull the pendulum off to one side and to a height of h above where it started, then we have performed work on the system to provide gravitational potential energy to the bob Earth system. If we then release the pendulum, this total amount of energy must remain constant. When the pendulum swings back through its lowest point, it will have kinetic energy equal to the amount of potential energy it started with. And then the bob will continue to swing until gravity reconverts all of the kinetic energy into potential energy. The bob can never achieve a height greater than where it started unless we come in and push it again. Halfway between the top and bottom of the pendulum's path, the pendulum will have an even split of potential and kinetic energy. If we know the height we started from, we can quickly determine the speed of the bob at any given point in its swing. As another example of applying conservation of energy, consider a roller coaster-like track. A roller coaster car starts from rest on the track, high enough that it completes the entire loop. If we call the bottom of the loop h equals 0, then, initially, the car-Earth system has potential energy equal to mgh, where m is the mass of the car and g is the acceleration due to gravity. As the car falls, at any given moment, the energy of the system will be a combination of the kinetic energy of the car and the gravitational potential energy, and eventually the car will rise again to the same height it was released from, assuming no non-conservative forces are at play. Our question will be how high must the car be released from to ensure that it completes the loop-the-loop. It should be obvious that if we release the car from rest at a height below the top of the loop, then the car will not complete the loop. If the loop has a height of 2r and we release the car from a height of r, then the car simply does not have enough energy to make it to the top of the loop without external help. A more reasonable guess would be to release the car from the same height as the top of the loop. Now the car has enough energy to reach the top of the loop, but because at the top of the loop the car's potential energy is the same as the energy it had at its release, the car no longer has any kinetic energy, so it stops moving at the top of the loop, at which point it is subject only to the force of gravity and will fall straight down. A thrilling but generally unacceptable end to a roller coaster ride. You may recall that a requirement of circular motion is the presence of a centripetal force and centripetal acceleration. A centripetal force is equal to mv squared over r, where v is the tangential velocity of the car. At the top of the loop, the only force acting on the car is the force of gravity, so gravity must be behaving as a centripetal force here. This means to maintain circular motion, the car has to have a speed of at least √gr. Kinetic energy is 1/2 mv squared, so in addition to the mg2r of potential energy, our car needs at least 1/2 mgr of kinetic energy. So we'll place the car higher, where its initial potential energy is mg2r plus 1/2 mgr for a total of 5/2 mgr. So the height at which the car must be released must be at least 5/2 r. This, of course, is assuming that no non-conservative forces are acting to remove the energy. As a final example, consider a block moving with some initial velocity. It approaches a hill, a patch of friction, and a spring. When the block ultimately reaches the spring, how much will it be compressed? We can choose some values for all of these variables, and then examine the energy of our system. We note that our block initially begins with entirely kinetic energy, and when it fully compresses the spring, it will have entirely potential energy, which will be split between gravitational and spring potential energy. Additionally, some work will be done by friction against the block, which will convert some of this mechanical energy into thermal energy. Rewriting this in terms of the variables we have, we begin with energy equal to 1/2 mv0 squared, we lose some energy equal to mu sub k times the normal force times the length of our friction patch, and we end with energy equal to the sum of mgh and 1/2 k delta x squared, where delta x is the compression of the spring. Conservation of energy tells us the energy the system starts with, less the work done by friction, will be equal to the work we end with. So we plug in our terms for initial energy, work done, and final energy, and solve this equation for the compression of the spring. Plugging in the numbers and making sure all of our units are consistent, we find that the compression of the spring will be about 17.5 centimeters.